Welcome to This Explainer. I am so thrilled you're here with us. Today, we're going to trace the absolutely incredible journey of a single photon. We'll start deep inside the fiery, chaotic core of the Sun, an environment of just unimaginable pressure where this photon is born. We'll follow it as it travels across the vast vacuum of space, taking an 8-minute sprint to our planet, and finally landing directly onto a solar panel right here on Earth.
Think about that for a second. Tremendous amounts of energy are constantly being created within our Sun, and honestly, only a tiny fraction of it ever actually reaches us. Yet, the amount of solar energy that hits the Earth's surface could easily meet the energy needs of the entire world many times over. So today, we're exploring exactly how humanity can tap into this ultimate power source. We're going to bypass the dense, heavy mathematics of thermodynamics and instead focus on visualizing exactly how light and heat really behave.
Okay, consider the number 1373. That is 1,373 watts per square meter, which is known as the solar constant. It represents the sheer, staggering volume of energy reaching the very outer edge of the Earth's atmosphere on a surface that's perfectly perpendicular to the Sun's rays. Just imagine a 1 square meter patch floating at the edge of space. It is constantly bombarded by nearly 1,400 watts of continuous power. To put that into perspective, it's roughly the equivalent of 14 super bright 100-watt incandescent light bulbs shining relentlessly on a space the size of a small desk. No way, right? But it's true. Here is our roadmap for today. 1. The ultimate power source. 2. Riding electromagnetic waves. 3. The ideal black body. 4. Earth's atmospheric filter. And 5. Absorbing and capturing energy. Let's dive in.
Section 1. The ultimate power source, inside the solar reactor. Our journey obviously begins at the Sun.
Now, it's incredibly helpful to stop thinking of the Sun as just a bright light in the sky and start picturing it as a massive continuous nuclear reactor. It's fueled by the relentless fusion of hydrogen atoms into helium. And what's truly fascinating here is the temperature drop. Down in the Sun's core, where that intense nuclear fusion is happening, temperatures reach an astounding 40 million Kelvin. Just imagine the violent collision of atoms happening at that heat. But as that energy radiates outward to the convective zone, the outer surface, it cools down significantly. By the time it actually leaves the Sun, the effective surface temperature is roughly 5,800 Kelvin. From that surface, the Sun is pumping out a total energy of 3.8 times 10 to the power of 26 watts. It's a number so huge it's almost impossible to picture. Out of all that outward radiation, less than a billionth of this energy actually strikes the Earth. But you know what? That tiny, infinitesimal fraction is all we need. It's the engine that drives our weather, grows our food, and holds enough potential to power our entire civilization.
Section 2. Riding electromagnetic waves, the language of light.
Once our photon leaves that 5,800 Kelvin surface of the Sun, it has to travel 150 million kilometers through the cold vacuum of space. And to understand how this immense energy travels, we have to look at the electromagnetic spectrum. Because solar radiation isn't just one type of light, it spans a really wide spectrum. About 39% of the Sun's energy arrives as visible light. That's the narrow band of colors from violet to red that happens to perfectly trigger the sensation of sight in the human eye. Isn't it amazing that the Sun's energy output peaks right exactly where our biological eyes are tuned to see? Meanwhile, about 9% of the energy is in the short, highly energetic ultraviolet, or UV range. Yeah, the stuff that causes sunburns. But the biggest slice of the pie, roughly 52%, actually arrives in the near-infrared region. This is completely invisible to us, but it is the exact thermal radiation we feel as heat when we step outside on a bright summer day.
Moving on to Section 3. The ideal blackbody, setting the radiative standard.
To accurately measure and eventually capture this mix of visible and infrared energy, physicists need a highly reliable baseline. So they use a theoretical benchmark known as a black body. A black body is basically the absolute gold standard in thermodynamics. By definition, it absorbs all incident radiation, regardless of the wavelength and direction. It's like a perfect sponge for light. And when it emits energy, it does so perfectly uniformly in all directions. At a specified temperature, literally no surface can emit more energy than a black body. It's the ultimate benchmark that scientists use to measure everything else against in the universe.
And this distinction brilliantly illustrates the difference between theory and reality. The Sun actually acts very much like an ideal black body at roughly 5,800 Kelvin. Its emission curve almost perfectly matches the theoretical math. But everyday objects on Earth are what we call real bodies. Everything around us, the chair you're sitting on, the walls of your room, the clothes you're wearing, they emit and absorb thermal radiation far less perfectly. Real bodies selectively absorb and reflect light based on their specific material properties.
And this selective behavior is exactly what gives objects their color. A green leaf, for example, reflects the green wavelength back to our eyes while absorbing the rest of the visible spectrum to perfectly fuel photosynthesis.
Section 4. Earth's atmospheric filter, the obstacle course.
As our photon completes its journey through the vacuum of space and finally reaches Earth, it doesn't just hit the ground intact. It has to successfully navigate a highly complex, layered obstacle course. Sunlight is significantly weakened or attenuated as it enters. First up, the ozone layer acts as a vital planetary shield, absorbing nearly all those harmful, short-wavelength UV rays. Second, the air molecules themselves get in the way. Because of their specific size, oxygen and nitrogen molecules scatter the shorter violet and blue wavelengths in all directions, which, by the way, is exactly why our sky looks blue during the day and why sunsets look brilliantly red when the sunlight has to travel through a much thicker slice of the atmosphere at dusk. Finally, atmospheric water vapor and carbon dioxide soak up specific bands of the long-wavelength infrared heat. By the time the sunlight finally hits the ground, that original 1373 watts per square meter has been reduced to about 950 watts per square meter on a clear day. Think about that. That's nearly a 30% loss of energy just from passing through the atmosphere.
Now, this atmospheric filtering creates a fascinating and highly consequential phenomenon. Have you ever wondered why a parked car gets so dangerously hot in the sun? Well, it's because the glass is transparent to the shortwave visible light coming from the sun, but it's completely opaque to the long-wave infrared heat that the car's interior tries to radiate back out. The heat gets entirely trapped inside. Our atmosphere's greenhouse gases, like CO2 and water vapor, do the exact same thing but on a massive planetary scale. They let the visible sunlight in, but block the Earth's emitted infrared heat from escaping back into space.
Section 5. Absorbing and capturing energy, the landing pad.
The surviving solar radiation finally lands on Earth. What happens next depends entirely on the specific material properties of whatever it strikes. When radiation hits a surface, the energy basically splits into 4 distinct pathways. First is absorptivity. That's the fraction of energy a material soaks up, kind of like a dark asphalt road baking in the summer. Then there's reflectivity, which is what bounces off, exactly like light hitting a bathroom mirror. Next is transmissivity, the energy that passes straight through, like sunlight shining through a clear glass window. And finally, emissivity, which is how well that material radiates its own heat compared to our theoretical blackbody standard. The first law of thermodynamics strictly requires that whatever is absorbed, reflected, and transmitted must perfectly equal the total incoming incident radiation. And engineers, they absolutely obsess over these exact variables to harness the sun's power.
Just look at how brilliantly we can manipulate these properties to bend thermodynamics to our will. To build a highly efficient solar collector, engineers need a material with high solar absorptivity but low emissivity, meaning it drinks in the sun's heat but stubbornly refuses to radiate it back out into the air. Black chrome is a perfect heat trap for this, absorbing 87% of solar radiation while emitting almost nothing. This is exactly what you want when you're trying to boil water with sunlight. Conversely, if you want to keep something like a fuel tank or a refrigerated delivery truck cool under the blazing sun, you want the exact opposite, aggressive heat rejection. So, you'd use white acrylic paint or anodized aluminum, which powerfully reflects the sun's rays but has a really high emissivity to rapidly shed whatever minimal heat it does end up absorbing. We literally design these selective surfaces to control energy flow. And that brings us to the end of our journey today. Understanding how a single photon travels from a 5800 Kelvin star, navigates a dense atmospheric filter, and lands down onto a specially coated panel isn't just dry physics. It is literally the blueprint for our clean energy future. The numbers and physical realities we explored today govern the single most powerful energy source available to humanity. So, as we continue to master the exact radiative properties of new materials, what next massive breakthrough in renewable energy will we engineer? I'll leave you to think about that. Thanks for joining me on this explainer, and keep learning.